Okay, so last time we talked about independent and dependent events and then also multiple selections here. Okay, so let's go ahead and make up some problems that you guys could work on here. So I'm going to make up a contingency table. So let's say we're looking at a class here, took statistics, English or history. So I did a little survey and we figured out who passed, who did not pass. There we go. And let me just fix this up here. Okay. And so let's say we had 26 statistics passed, 8 did not, 32 passed their English, 4 did not, and then 25 passed the history, and 12 did not there. Okay. And we're going to go ahead and select one person here. And we want to find, and let's put a couple of these things here. So the probability that they took statistics. Let's put another one up here. Let's say the probability they took English. No, write that a little faster here. They took English and passed. And how about the probability they took English and history? But let's put a little kind of subnote here. Let's pretend they're only allowed one class per session. So let's pretend this is like a winter session or something, and they were only allowed to take one class at a time. Okay, so probability they took English and history. Probability that they took history or actually and did not pass. Probability they took statistics or English. And then here's a few more. And I changed problem D right there if you didn't catch that. It's a or. Did not pass. Let's leave it as an or. Let's just write all of these up here. So what if we selected 3 people, the probability they all passed, and we're going to treat as dependent, and then the probability they all took history, and let's treat that as independent. And let's also name 2 events that are mutually exclusive here. From our table. And let's put one more in here. How about the probability they pass given they took statistics? And I think this is going to probably summarize everything we've done here. So again, let's say this is a session. They're only allowed to take one class. Go ahead and pause the video and try to answer some of these here. And I would suggest first make the totals on your table. Okay, so you had a chance here to try some of these out. And first thing I do is I always put the totals here. And it's a good habit to add them vertical and horizontal and make sure you get the same number both ways. That's always a good check. So the probability they took statistics, I'm going to use probability of S. Okay, so P of S. And so my total statistics here, again, these are going to be our total columns right here at on the edge there. So this is going to be my total this way, and here's my total this way. So statistics, the grand total is going to be 34 out of that 107 that we have there. And I know WebAssign has been asking to reduce, but we're just going to go ahead and write it to 4 decimals there. Okay, probability they took English and passed. So our notation here is E and P, let's put. And we're going to have 32 out of 107. And so where this is coming from is we're doing an AND case here, so 2 different events. So probability they took English, which is going to be this guy here, and they passed, which is going to be this way. So since it's an AND, we're looking for that intersection. So it's 32, and again, out of our grand total. So 32 out of 107. And again, to 4 decimal places, get about 2991. Okay, probability they took English and history. So another AND case. And so what's happening here, though, is notice that these guys don't go perpendicular like English and past. Those guys had a crisscross. These two are going the same way. So this is going to be English and history. And notice there is no overlap. There's nothing that they share in common because they're both going horizontal. So it's going to be 0 out of the 107 in this case. And that's because these events are mutually exclusive. You can't be in both. You're either in one or the other. And to 4 decimals, that gives us 0. Probability they took history or, and if you recall, I changed that. So or did not pass. And here's the formula. But we're going to do it a bit more intuitively without the formula here. And so probability that they took history is going to be this group right here. And so we're looking at our history in this case. And that's where that 37 comes from. And again, out of the total. The 24 is coming from because now that they did not pass, so we're looking at this whole group over here, did not pass. And so that's going to be our total, 24. But we have to subtract any overlap that we have between these. So again, we're saying history did not pass, and this group here now ends up being an overlap. You counted them when you counted the history, and you counted them again on the not pass. So those 12 we're going to have to subtract because again, we're crisscrossing, going vertical and horizontal. And so that's where those 12 are coming from. And again, to 4 decimal places here. I'll clean up the fraction first. And we get this. Okay, probability they took statistics or, so now the key word is or here. They took statistics or English. And for the or case, we always have the formula here. And so probability they took statistics is going to be this group right here. Probability they took English is going to be this group right here. So we're going to end up with 34 and then 36 in this case. And notice there's not an overlap between those two. So we're going to have 36 out of 107. And notice I did not have to do this other portion here of subtraction because there is no overlap. If you recall, they both went horizontal there, right? So there was no overlap. That's just going to be 0. So we're just going to worry about those two. We get 70 over 107. And again, to 4 decimals, about 6542. Probability they pass given they took statistics. So probability they pass given they took statistics. Let me write that there. So this is a tricky one where you don't go out of the total. So if I'm giving you a hint, I'm saying given they took statistics, this is all I'm looking at. That is my whole new table, and I could kind of forget about the rest now because I'm giving you that hint that they took statistics. Now, out of those that took statistics, how many of them passed? 26 of them. So it's 26 out of the 34. This is the only time we don't do it out of the grand total whenever we say given, because we're limiting it to a small section there. So we're going to get 26 out of the 34. Now, you don't want to think about it this way. I mean, you kind of could. It's not that correct, but think of this little slash here as a division. So I'm dividing in the denominator those who have statistics, which is a 34. And then on top, from that group here, those that actually ended up passing is going to be those 26. So you could think of the given as kind of a fraction if that helps a bit. Technically a little incorrect, but if it helps out, that's fine. And again, to 4 decimals is going to be 7647. There we go. Okay, now here we're going to select 3 people. So now we're talking multiple selections. So we're no longer going to use the addition rules. We're going to now start using the multiplication rules. So probability that they pass and treat as dependent. So dependent means it matters what happened before. So let's think about this as 3 different people. Let's talk about the first person. Probability the first person passed is going to be 83 out of 107 here. So here's our past. So 83 out of the grand 107. Okay. Now, since we're treating it as dependent, that person is thrown out of there now. So there's no longer 107 people. There's now going to be 106 people. But I also took out one of the people that passed, right? That person I threw out passed. So I no longer have 83 of them. I now have 82 of them. So the next one is going to be 82 out of 106. Now for the third selection, again, 2 of those people are out. So I have 81 that ended up passing out of 105. That's the grand total. Since it's multiple selections, I'm multiplying these events. So just multiply these guys. And to 4 decimals, we should end up with that. And sorry, little ring in the background, but we're just going to keep moving. All right. Probability that they took history and treat as independent. So again, history, 37 out of 107. That's the first person that we're going to select. Now, since it's independent, that means we're putting that person back. So again, when you pick the second person, there's still 37 out of 107. We put that person back again, and then we go and we select one more time, and it's still 37 out of 107. So the independent's the easier case because we don't got to keep track of that. A nice way to write this on your calculator would be 37 out of 107 cubed, right? So to the power of, and you could use this caret key on your TI. That's what means to the power of. And you get 0.0413. Or you can multiply them by themselves. Now let's name 2 events that are mutually exclusive. That means that they cannot occur at the same time here. So how about past and not past? Okay. Those guys, you're either in one group or the other. You are not allowed to be in both of those. So past, not past. Some other mutually exclusive groups, well, just go the same way. Don't crisscross. So statistics and history, those guys are also mutually exclusive. English and statistics are mutually exclusive. However, if I crisscross this way, these guys are not mutually exclusive. Statistics and not past because there is an overlap in that case. All right, let's keep going here. And let's talk about tree diagrams and how to actually get some sample spaces from there. And we could also use this to help us with multiple selections and the multiplication rule. So tree diagrams kind of a nice way for us just to kind of get some pictorial, some pictures going here. And sorry, got some noise in the background here, but I'm trying to access this image. Okay, so let's do a simple example. Let's say I have 3 red, 4 blue, and 1 green marble in a pot. And I want to select 2 marbles here. And we're going to do this with replacement. Okay, so we're going to pick 1 marble and then the second one. So let's talk about our very first selection here. What's possible for us to actually get? Well, you could get a red marble, you could get a blue marble, and you could get a green marble. Now let's talk about the second selection. Well, on the second selection here, we're doing this guy with replacement here. And so if I put the marble back, again, on the second try, we're going to have with red, blue, or green. And let me just put that note there. This will always be given to you if we're doing it with replacement or with not, or if it's independent or not, or dependent. So then for the second trial, you could also get red, blue, and green, and then you could also get red, blue, or green again. So this is kind of our tree diagram here of the outcomes. You could kind of follow the different limbs. Okay. So my sample space would end up being all of these combinations. So I could get red, red, and so that's if I follow this path right here. I could also get red, blue, and that's if I follow this path right here. And I could also get red, green, and that's going to be if I follow this path right here. And same thing for all these others. If I pick one of these paths, like here, that's going to end up giving us blue, green. And so we follow all the different paths on our tree diagram, we're going to be able to get our entire sample space. Okay. We also want to be able to write probabilities here. So the probability that we get a red marble on that first selection, well, there's 3 red marbles out of a total of 8. So 3/8. And we just write the probability there on kind of that limb. Probability we get a blue, well, there's 4 blue out of the 8. And probability we get a green, there's 1 out of those. Now, if we're putting this back with replacement, it starts all over. So this is the easier case. Probability I get a red one on the second try. So that means when I selected that marble, I threw it back in. So when I shake it, it's starting over again. It's still going to be 3/8, 4/8, and 1/8. And this is going to happen for all of them. But if we want to focus on the probability then of one of these routes right here, that would say we get red, red. Since it's multiple selections, we're just going to multiply. It's going to be 3/8 times 3/8. And that's going to end up giving us 9 out of 64. Probability I get a red and then a blue, so I'm following this path right here. So I'm going to multiply 3/8 and 4/8 this time. Multiple selections, just taking each one. So red and then blue. That's going to give us 3/8 times 4/8. And then probability, we get red and green. And again, we're following this path, so that's going to be 3/8 times 1/8. And we typically want to turn these to 4 decimals. I'm just going to leave them as a fraction right now so we could kind of see where it came from. And we're going to do this for each of those, right? For the second draw, it's going to be exactly the same. Still 3/8, 4/8, and 1/8 because we're putting them back. And we could follow our tree diagram to not only get the sample space, but to actually get the probabilities of each of those different outcomes as well. So if I pick one of these at random right here, let's do this next one. So probability that I get a blue and then a green. So here's blue and then a green. It's going to be 4/8 times 1/8 because we're following this path right here. So blue and then green. And we're just going to multiply those probabilities times each other. That's what the multiplication rule tells us. And there we go. And so this is going to be our complete setup. And from this, we could start answering all kinds of questions that we need to. But this is a tree diagram with a sample space and their corresponding probabilities. Okay, so let's look at the trickier case. What if we wanted to make a tree diagram but without replacement? So this means once I select the marble, it's going to be gone. I'm no longer going to end up having it there. Okay. So without replacement here. And let's do the same thing. Let's write the sample space with the probabilities. And I encourage you to pause it here and then go ahead and try this tree diagram on your own. Okay. So our first selection, we could still get any of the three. We could get red, blue, or green. For the second selection, if we get a red, there's still a red, blue, or green possible. If you get a blue, there's still a red, blue, or green possible. But there's only one green. So if you select a green, it's no longer there. So for the second trial, you could only get a red or a blue. There's no longer a green to actually get there. And I'm just going to move these over a little bit there. So my sample space is going to end up being all of the different paths here. So red, 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 blue, red, green, blue, red, blue, 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 green, green, red, and green, blue. There's no way to get a green, green because there's only one green there. And let's put the probabilities. So for the first selection, it's kind of the same thing, 3/8. But for the second trial, notice that I no longer have a red. So when I go to get another red here, so we're looking at this one here, there's only 2 reds left. Okay, and there's 7 total there. Okay, and same thing for the blue now. All the blues are still there, but there is one less overall. So there's 4, 7 blues there. And then for the green is still there, but you have a total of 7 marbles because one of them got taken out. That red one we removed, we put in our pocket, we didn't put it back there. And let's do this for the other ones as well. So 4/8 and 1/8 on the first selection. But let's follow this tree diagram here. So if I get a blue and then a red, well, all reds are still there, but I have one less marble overall. If I do the blue, blue, I have one less overall, but I also have one less blue. And same thing happening here now. So one less overall, but I still have all the green marbles. And we'll go ahead and do this for the other one as well. Okay, so we could go ahead and write the probabilities if we want here, but let's actually just focus on some questions here. So what is the probability here you get the same color? And so we're looking at the second one here without replacement. So what's the probability that we get the same color? So if we want the same color then, and then let's do one more question. What is the probability you get a blue and a red marble? So blue and a red marble. Okay, and you could pause and try these out if you want. Okay, so if we want the same color, that means we're going to get red, red, blue, blue, or we could actually get green, green, right? But we know that there's no way to get green, green because there's only one green marble. So the probability to get red, red here, let's just follow the path. That's going to be this path right here leading us to red, red. So that's going to be 3/8 times 2/7. And then blue, blue will be this path right here. So 4/8 times 3/7. And sorry, I want to sorry, did a slight adjustment there. Okay, and so we get 3, 2, 1, 4. Let's look at this one. Probability that we get a blue red or a red blue, because I didn't say the order. We just want to get a blue and a red one. So both of these we got to follow. So we're going to have to look at the blue red case, and we're also going to have to look at the red blue case as well. And so those probabilities are going to be 4/8 times 3/7, and then 3/8, 4/7. Again, because we're looking at these paths of blue, red, and then we're also looking at the path of red, blue. Okay, and to 4 decimals. All right, and I think that was a bit long there. I'll see if I could trim this up a little bit.